Hello, welcome to Lecture 6, Part 1 for Life of the Universe. Uh, I only just now had the idea of actually putting this slide into these lectures so I remember what part of what lecture I'm in, which is useful when I'm starting. So we're going to be continuing with our long Unit B on the plurality of worlds. This part will be about Kepler. But of course, as the first video of a lecture, that means we have an alien to have a little fun with first. And so here we have the Predator from the Predator franchise. And I'll have a link in the description so you can go listen to some music from the soundtrack if you'd like. Uh, for an actor in a suit, I think this is a pretty decent alien design. Especially, this is one of the first movie TV aliens to give it really funky looking mouth parts, which was a good idea. And however, some pretty good astrobiology in the Predator movies is when you see the Predator point of view. Their vision is not the same part of the electromagnetic spectrum as ours, which is nothing at all unexpected. In fact, we would kind of expect that to happen. Do have a little complaint with it, though, is he doesn't seem to have very high resolution vision, which a general predator should have sharper vision than they seem to. Incidentally, a little bit of fun with this particular movie is that I'm sure nearly all of you are aware that the star of the movie, Arnold Schwarzenegger, was governor of California for a couple of terms. But he's not the only actor from that movie who later became a governor. Jesse Ventura served a term as governor of Minnesota. And I don't know if he had time to bleed when he was governor, but he didn't when he was in the movie. But actually, that's not quite all. Though Arnold and Jesse were the only ones who successfully became governors, Sonny Landham ran for governor of Kentucky unsuccessfully in 2003. So since this is an election year, I'm just wondering, do we have another future governor from the Predator franchise? I guess we'll have to wait and find out. All right. On with our next major historical figure, Johannes Kepler, born and lived in most of his life in what is now Germany, then part of the so-called Holy Roman Empire, though he did live in Prague for a while. Turns out to be rather important. Kepler was not alive during a pleasant time to live in Central Europe. The last dozen years of his life overlapped with the first dozen years of the 30 Years' War, which lasted from 1618 to 1648. Presumably, they only named it the 30 Years' War after it was over. This war started as the dispute over who the next king of Bohemia would be, but it ended up, hold on. Stop. I'll shoot you. That threat I just made was against my cat, referring to a use of spray bottle because he was scratching my chair. So 30 Years' War grew into pretty much a continent-wide war, largely along religious lines, with Catholic countries mostly on one side, Protestants on the other, although it didn't quite entirely break down that way. It's at least one country that switched sides. The Turks were involved. In any event, in relative terms, it's the worst man-made disaster to hit Central Europe. Not in absolute terms. In absolute terms, the 20th century had some things that were worse because World War I and World War II. But in the 20th century, there were more people to kill in absolute terms. In relative terms, somewhere between about a third and half the population of what's now Germany perished during those 30 years. Kepler, I guess, maybe was a little bit lucky that he didn't see quite all of it. Kepler also problem living during that time. His mother was accused of witchcraft, the 1600s being the big century of the witch hunting craze. And anyway, Kepler was involved in her defense, and she was actually acquitted. I don't know how often that happened, if you were actually accused of witchcraft. Anyway, Kepler started out his working career as a rather poor teacher of mathematics. Apparently, the way a lot of colleges and schools worked at the time is they didn't actually pay their faculty a salary, but instead said that, okay, you want to give some classes, that's fine. Here's a classroom you can use. The students will pay you. And so the students would pay a fee directly to their instructors. Now, with this system, I've got 96 students this semester. If each one of you, basing it on a full load, would pay me directly 1/5 of your tuition and general fees, I would do better than I'm doing now. But I have core classes. Kepler didn't have that option or that incentive for people to take his classes, so he didn't do very well. But then after Tycho moved to Prague, he got a job working as Tycho's assistant, and Tycho put him to work trying to come up with a new model for detailed mathematical model for the motions of Mars. He knew Kepler was a Copernican, however, so he didn't give Kepler all the data. Then Tycho died suddenly. I guess if it had been a Thursday afternoon, Tycho could have taken a 3-day weekend. But anyway, Kepler took advantage of this to liberate Tycho's data notebooks, along with some of Tycho's scientific instruments. Tycho's family sued Kepler to get the stuff they said he stole back, and they got the instruments back, which was what had some monetary value. But Kepler kept the data books, which is what had the real value. And he then labored for quite a while trying to do different combinations of circles. And finally, he came up with a model he realized was the best he was going to do with circles, and it was really good. Most of the predictions of the model were spot on Tycho's observations. A few were off a little bit, but no more than about 8 arc minutes. Now remember that Copernicus and Ptolemy's model could only predict positions to a degree or two, 60 to 120 arc minutes. So precision of 8 arc minutes is way better than that. However, Kepler knew Tycho's observations were good to 1 to 2 arc minutes. So he did something really radical. He said, I know these observations are good to 1 to 2 arc minutes. Using circles, I can't get closer than 8 arc minutes. Maybe I shouldn't be using circles. And at that moment, we get that additional ingredient we need, besides nature working according to natural laws, that we need for modern science. And that is this, that any theory has to make a prediction about what will happen if you do an observation or do an experiment. And if you compare the results of that observation or experiment, assuming it was done correctly, which is why we require it to be repeatable. But when you compare experiment observation to the theory, if within the experimental uncertainty, they don't agree, the theory in its current form is wrong. And maybe a relatively minor tweak to the theory can fix it, but sometimes you got to throw the whole thing out. And in this case, what's being thrown out is the insistence that heavenly motions had to be combinations of circles. And this criterion of falsifiability is what most working scientists would say distinguishes science from non-science. Not that science gets you directly to the truth, but because science is a very good technique for identifying what is wrong, You don't have to keep wasting your time on those wrong ideas. And you can therefore get a progressively closer and closer approximations to whatever the truth actually of how the universe actually works is. Now, it's this ability to identify conclusively these wrong ideas as to what makes the non-scientific branches of knowledge not scientific. So let me give you an example. I will now attempt the deepest excursion into theology I will attempt for you. There's a book in the Old Testament known as the Song of Songs, sometimes the Song of Solomon, because Solomon is supposedly the author. And if you look at it, it seems kind of an odd thing to include in the Bible. God is not mentioned anywhere in it. It doesn't seem to be obviously theological in any way. On the face of it, it just seems to be a very good and actually very erotic poem. So why is it included in the Old Testament? Well, Jewish theologians will say that it's an allegory of the relationship between God and the people of Israel. Christian theologians will say it is that, but it is also an allegory of the relationship between Christ and the church. Some Muslim theologians argue that because one of the Hebrew words in it sounds kind of like Muhammad, it's a prophecy of the prophet to come. I don't know, I guess a Viking theologian, if you could find one, would say, no, this doesn't have anything to do with dying gloriously in battle so we can go to Valhalla in the afterlife. Cynical atheist might just say it's because it was popular and attributed to Solomon, so when the Old Testament was compiled, they felt they had to include it. Is there any experiment or observation we can do that will help us with any of this? Well, I can think of one in principle, but it's not repeatable, so it doesn't count. And that is you can die. And after you die, based on the nature of the afterlife, you can presumably rule, if any, you can rule some of those ideas out. So for example, if after your death you show up at the doors to Valhalla, then I guess we know the Viking was right, but I particularly have some doubts about that. Now, nothing wrong with theology in its realm, but it's not science. And it lacks that ability to conclusively identify ideas that are wrong, so you don't waste your time with them anymore. Well, anyway, back to our friend Kepler. So once he realized he had to get rid of circles, he tried other shapes, and eventually he found one that worked. Would predict positions that were in proper agreement with the observations. And this leads us to Kepler's first law, which he published in 1609. The orbits of the planets are ellipses with the sun at one focus. So let's learn a little bit about ellipses. But first, before that, let's think about a circle a little bit, shown on the right. Now, if I ask you to define a circle, most people would probably come up with something like what Supreme Court Justice Potter Stewart said about pornography. He couldn't define it exactly, but he knew it when he saw it. So, and most people think that way about circles. We know them when we see them. But it turns out we can define a circle precisely. It's the set of points in a plane that are all some constant distance, in this case r, from some reference point. That reference point is the center of the circle, and that distance is the circle's radius. Well, with an ellipse, instead of using one reference point, we have two. One, they're called, individually, they're called a focus, foci, plural. And the idea is any point on the ellipse, if you look at the sum of the distances between that point and each focus, that is a constant. And if you imagine taking the foci of an ellipse and move them really, really, really close together so they're at the same place, then what you would get would be a circle. So you can think of a circle as a special case of an ellipse where the foci are at the same point. Okay, here's a little bit more about elliptical orbits. So Kepler's first law has the sun at one focus. There's nothing at the other focus, so I have just a gray spot so we know where it is. This means the distance between the Earth and the sun, or the planet, any planet and the sun, changes. When it's at its closest, we call that closest point perihelion, which comes from Greek meaning close to the sun. Opposite side of the ellipse, point furthest from the sun, is aphelion, which comes from Greek meaning far from the sun. The way I remember which one is which, aphelion starts with A for away, perihelion doesn't. All right. The entire distance across the ellipse, perihelion to aphelion, the longest distance, that total distance is the major axis. Half of that distance, indicated by the red line here and labeled A, is the semi-major axis. And you can think of the semi-major axis as kind of like a radius for a circle. It tells you how big the ellipse is. Now, another useful parameter for an ellipse is its eccentricity, denoted usually by a lowercase e, which is a measure of how stretched out it is. So a circle would be an eccentricity of 0. At another extreme, if you imagine taking aphelion and moving it infinitely far away, you stretch the ellipse out into a parabola. And E equals 1 is a parabola. So a proper ellipse would be E somewhere between 0 and 1. And the one I've shown here, it's actually pretty high. It's about 0.7. That is much more eccentric than the orbit of any of the major planets. Mercury is the most eccentric at about 0.2. Then Mars at about 0.1. Earth is not quite 0.02. So we're pretty close to a circle. Actually, it's pretty lucky that Kepler was working with, had the best data for Mars from Tycho Brahe, because Mars's orbit is eccentric enough where the data was good enough to show that. If it had been Venus, the eccentricity of Venus's orbit is less than 0.01. Tycho Brahe's observations wouldn't have been good enough to show that Venus's orbit is not a circle. Right? Some of the smaller things in the solar system, asteroids and comets, can have significantly larger eccentricities than the major planets, and significantly larger than 0.7. All right, now there's also a second law, which I don't think I put a slide in here about. Yeah, I did not. I'll just briefly mention the second law and go back to the slide while I'm talking about it. The second law is not so critical for us. With the second law, also published in 1609, it's about how fast the planet moves at different parts of its orbit. It moves faster at perihelion, slower at aphelion. So, but as again, like I said, that's not incredibly critical for us, so we won't worry about it here. One thing that is very important for us, though, is Kepler's third law. And anyway, Kepler realized pretty early on that there had to be a relatively simple mathematical relationship between the size of a planet's orbit and this semi-major axis and its orbital period, how long it took to go around the sun once. But it took him another 10 years of trial and error to find it, but he did. He published it in 1619. We now call it his third law. And it's a statement that the square of the orbital period of the planet is proportional to the cube of the semi-major axis of the orbit, which we could write as a little equation: p squared equals some constant that we'll call k in honor of Mr. Kepler, times the semi-major axis cubed. All right. The value of k will depend on our choice of units. So astronomers, like everybody, we like to make our lives easy for ourselves. So if we're clever, we can make k very easy to deal with. So let's suppose that p can be any unit of time, so let's use years. A has to be in a unit of distance. There's a unit called the AU, which is short for astronomical unit. It's distance between the Earth and the Sun, that is convenient to use here, so we'll use AUs. And if we pick these units, the Earth's orbital period is 1 year, and our semi-major axis of our orbit is 1 AU. 1 squared is 1. A cubed is only slightly harder calculation than 1 squared. 1 cubed is 1. So that gives us 1 equals k times 1. So as long as we use these units, K is just equal to 1, and Kepler's third law just becomes p squared equals a cubed. In this course, almost every time we need to use this, these will be the units we'll be using, and K will be equal to 1. In the planetary exploration project, there will be one instance where other units are more convenient, but I will tell you the value of K for that other set of units when we get there. Now, let me work out an example for you. Kepler's third law, in the form we've just done it, works for anything orbiting the sun. And let's see how it might work for Ceres. Largest object in the main asteroid belt, now called a dwarf planet, discovered in 1801, long after Kepler's death. Anyway, its orbital period is 4.6 years. So let's find the semi-major axis. Okay, we don't really have to, but it is traditional to write the thing we're trying to find on the left side of the equation. So turning the equation around to be a cubed equals p squared is a good place to start. And then the problem is we've got a cubed and we need a. So we convert a cubed into a by taking the cube root of it. But if you do something to one side of an equation, you've got to do it to both, or else it's not an equation anymore. So we've gotten then the cube root of p squared on the right. All right, now, you may have a calculator with a cube root button. If great, you can use it. But if you don't have one, you can still calculate that as long as you have a button that will let you raise a number to any arbitrary exponent that you want. That button will either typically be a y to the x or a little thing that looks like a little rooftop. And anyway, we can do this because of a really cool property of exponents. It turns out that taking the third root of something is the same as raising it to the 2/3 power, or rather to the 1/3 power, the cube root. But because p is squared and we're taking the cube root of it, the combination of the squaring and the cube root is raising p to the 2/3 power. So you take the 4.6, raise it to the 2/3 power, do the calculation right. The number rounded off a bit will be 2.77, and units are AUs because we found A in a Kepler's third law problem. All right, I'll come out of the share for a second. Say something about units. All right, right here, I've got a quarter, right? If we were in class, I would ask you if anybody would give me $25 for this quarter. In more than 20 years of teaching, nobody has taken me up on it, okay? And the reason why none of you have done that yet is because you understand units when it comes to money. 25 cents is not the same as $25 because a dollar is a bigger unit of money than a cent. Now, unit mistakes can be far more costly than $24.75. Back, I want to say late 80s, early 90s, sometime around there, there's a spacecraft called the Mars Climate Orbiter. You can guess from the name of it, it was supposed to go into orbit around Mars to study Mars's climate. As it was approaching Mars, it had to slow down, so Mars's gravity could capture it in orbit. And so they had to fire the rockets on the spacecraft to slow it down, okay? Engineers for a contractor with NASA calculated, okay, you need to fire this thrust for this length of time, provided that data to NASA, who then sent the commands on to the spacecraft. However, the data provided by the contractors, the units were in, the thrust was in force units of pounds, unit of force in the British system of units. NASA sent the command to the spacecraft as if those numbers were in units of newtons, the unit of force in the metric system. This is really a mistake at the level of don't, but because of that don't level unit mistake, instead of going into orbit around Mars, a $200 million spacecraft burned up in the Martian atmosphere. It could have been worse. That could have been a manned mission, in which case the crew would be dead. Nature does not give partial credit. So pay attention to units. All right, back to the share. Now, there in the practice exercises for this unit, I've got some more Kepler's third law things you might want to, definitely I think should want to try. That's right, I always have to click on that, come back in. And here's a caution. MIDI calculators these days will let you enter a number or a calculation all at once, and then it equals or enter or solve or whatever. So you might be tempted to solve that problem by having this display on your calculator. If that's what's on your calculator, I pretty much guarantee you the answer will be wrong. And that is because calculators are very stupid machines. They do exactly what you tell them to do, not what you want them to do. And there's something called order of operation where exponents take priority over multiplication and division. So if you tell it to do what's here on top, then what it will do is it will square 4.6 and then divide the result by 3, which is not the same as raising 4.6 to the 2/3 power. If you want to make sure it does things in the right order, put the 2 divided by 3 in parentheses. That tells the calculator to divide the 2 by 3 before it does the exponent, and then it'll do what you want. Now, I should point out that Kepler derived his laws of planetary motion empirically, which means just a lot of trial and error, grinding through, fitting different mathematical relations to the data. He did not have a more fundamental physical theory from which they could be derived, but Newton was able to do that. All right, and then finally, the attendance secret code for this video. Kepler wrote a kind of a long short story, short novel called Somnium, which is Latin for dream, about a journey to the moon. And within this, Lavania was the name of the kind of fictional country realm of the moon that he went to. So that'll be our secret code for this video. This is a one of the earliest works of science fiction. And Kepler was actually very enthusiastic about the idea of extraterrestrial life. Okay, this has probably gone on for a while. So I'm going to stop the share here. But this is probably going to be a relatively long lecture because I'm going to do another video for Galileo. So if we end up going a little over the 50 minutes we'd be in class in person, don't whine because most of these lecture sets of videos are less than 50 minutes. So I'll see you in the next part for Galileo.